Hi, and welcome to this part 2 of the Learning from Disasters module. Just going to start with accident theories, but then lead on to things around reliability, structural integrity, and also testing to finish off with this section. So before I go into the input, should we say, I wanted to start with one of the CSB videos that's on YouTube. It's about 11 minutes long, but it just helps me explain, should we say, some of the issues around this and the importance of the human element again, which I focused a lot in part 1 of this session, but also the attitude of management and then the lack of resources and perhaps the maintenance, because a big part of part 3 is to look at the ineffectiveness of maintenance and how that can affect reliability. So there's that kind of balance going on. So without further ado, I'm going to go to our YouTube video. And I'm a big fan of the Chemical Safety Board and what they've done. They kind of like do an investigation and then pull it together.
Mgpi processing facility in Atchison, Kansas. An unintended chemical reaction resulted in a dense cloud containing toxic chlorine gas and other chemicals that drifted into the community, leaving over 140 people with reported injuries. The incident occurred during a routine chemical delivery when two incompatible chemicals, sulfuric acid and sodium hypochlorite, were inadvertently mixed, forming the toxic cloud.
Delivery and unloading operations may be perceived as simple compared to other processes at chemical facilities. But because these activities can involve large quantities of chemicals, the consequences of an incident can be severe. Our case study on the Mgpi incident stresses that facilities must pay careful attention to the design and operation of chemical transfer equipment to prevent similar incidents.
The Mgpi facility produces distilled spirits, specialty wheat proteins, and starches. The incident occurred in a section of the plant that uses sodium hypochlorite, or bleach, as well as sulfuric acid. These two chemicals, when combined, can form chlorine gas and other chemical compounds. On the morning of the incident, a truck from a chemical distribution company, Harcross Chemicals, arrived at Mgpi to complete a routine delivery of sulfuric acid. After reviewing paperwork in the control room, an Mgpi facility operator escorted the driver to a locked loading area. There, chemicals are transferred from trucks into the facility through piping called fill lines to several large storage tanks in an outdoor tank farm. The Mgpi operator unlocked the sulfuric acid fill line for the driver to connect the truck's unloading hose. The operator remembers pointing out the correct fill line to the driver before he returned to his workstation. The driver, however, does not recall hearing the operator identify the fill line. Unknown to the operator, the sodium hypochlorite fill line was also unlocked, and the two lines, which were only 18 inches apart, looked similar and were not clearly marked. The driver connected his truck's sulfuric acid hose to the sodium hypochlorite line, and sulfuric acid began flowing inside. He then returned to the cab of his truck. Shortly before 8 a.m., a greenish-yellow gas began flowing from the bulk tank of sodium hypochlorite. The driver noticed the cloud in his truck's side view mirror and attempted to return to the connection area to turn off the flow of sulfuric acid, but the gas overwhelmed him. He then ran to the passenger side of the truck to close a valve that could halt the flow, but he was prevented from doing so by the gas. Instead, he ran away from the cloud and escaped to a separate area of the facility. At about the same time, toxic gases entered the facility control room through the building's ventilation system. Mgpi operators preparing for shift change in the control room were immediately overcome by the toxic gas. Because the operators had a practice of locking respirators between shifts, some were unable to access their respirators before evacuating the building. With no other way to stop the flow other than closing manual valves on the fill line or truck, or by triggering one of the truck's emergency shutoffs. The sulfuric acid continued to enter the sodium hypochlorite tank for nearly 45 minutes until emergency responders shut down the flow. Approximately 4,000 gallons of sulfuric acid combined with 5,800 gallons of sodium hypochlorite, causing a large, dense cloud containing chlorine gas, which soon drifted off-site. Mgpi employees were evacuated from the site, and 11,000 adjacent citizens were advised to either shelter in place or evacuate. Over 140 people, including Mgpi employees, emergency responders, the truck driver, and members of the public, sought medical attention, some requiring hospitalization.
Chemical distribution takes place on a massive scale in the United States. According to a study by the National Association of Chemical Distributors, more than 39.9 million tons of product were delivered to customers every 8.4 seconds in 2016. The CSB is concerned that there are many opportunities for incidents like the one at Mgpi to occur.
John Hennigan is director of the Pipeline and Hazardous Materials Safety Administration's Hazardous Materials Safety Southern Region Enforcement Office.
According to our data from 2014 through 2017, unloading incidents involving hose connections to incorrect tanks occur frequently. These incidents are often quite serious because of the large amount of chemicals involved. Most commonly, the incidents involve compatible materials and result in tank overfills. Incidents similar to the one at Mgpi, where two incompatible materials are inadvertently mixed and result in a chemical reaction, occur less often, but are nonetheless problematic. Since 2014, 8 incidents similar to Mgpi have occurred. These incidents resulted in 44 injuries and the evacuation of 846 people.
In its case study on the Mgpi incident, the CSB identified several human factors deficiencies, which influenced how the operator and driver interacted with the chemical transfer equipment.
Chemical facility operators and delivery drivers often work directly with chemical transfer equipment for loading and unloading operations. Study of human interactions with process equipment, called human factors, should be carefully considered when identifying hazards, particularly because chemical delivery drivers may not be familiar with the facility's equipment.
For example, at Mgpi, the CSB found that the close proximity of the sulfuric acid fill line to the sodium hypochlorite fill line increased the likelihood for workers to make an incorrect connection during chemical unloading. The CSB also discovered that the two fill lines looked and functioned identically, using the same type of connections. Lastly, the CSB found that of the 5 fill lines in the unloading area, only one was labeled at the point where the hose connected.
A key lesson from our case study is for facilities to evaluate chemical unloading equipment and processes and implement safeguards to reduce the likelihood of an incident. This should be done while taking into account human factors issues that could impact how facility operators and drivers interact with that equipment.
This can include physically separating fill lines by a discernible distance, selecting hose couplings and fill line connections with unique shapes or colors for each type of chemical, and ensuring that fill lines are properly labeled. Also, during its investigation, the CSB found that at the time of the incident, Mgpi did not have instrumentation that could automatically shut down the transfer of chemicals from the unloading area in the event of a process deviation. Since the only ways to shut down the transfer of sulfuric acid to the sodium hypochlorite tank required human interaction and were located within areas affected by the release, there was no way for workers without proper personal protective gear to stop the flow once it began.
Another key lesson from our case study is for facility management to evaluate their chemical transfer equipment and processes, and where feasible, install alarms and interlocks in the process control system that can shut down the transfer of chemicals in an emergency.
Finally, the CSB found that Mgpi's procedures were not aligned with their work practices. On the day of the incident, the operator was not present when the transfer hose was connected to the fill line. Even though the company's procedures state that operators must verify the connection and that the operator should be the one to open the fill line valve, But the CSB discovered that some operators were not aware of these steps in the procedures, and that it was their practice to have drivers open the fill line valve, thinking this would be safer, since drivers wear personal protective equipment in the event of a release.
A third key lesson from our case study is for facilities to work with chemical distributors to conduct a risk assessment and then develop and agree upon procedures for chemical unloading to ensure responsibilities are clearly defined.
As the Mgpi incident demonstrates, although unloading operations are relatively simple compared to many of the complex processes taking place in chemical facilities, the consequences can greatly impact workers and surrounding communities due to the large amounts of chemicals transferred during deliveries.
Chemicals are transported and delivered every day all around us. Because these deliveries are so common, the CSB strongly urges the managers of facilities and distributors to review and adopt the key lessons from our case study and work together to prevent future incidents like the one at Mgpi. Thank you for watching the CSB safety video.
For more information on the CSB's investigation.
So, like I say, I'm a fan of the CSB because they do these animated interpretations of an investigation and the learnings from it, which is great. But it also helps us, should we say, in terms of how we use that information. And you could perhaps see some similarities with other disasters. And when you look at statistics, there's been 4 other similar incidents that took place in a period of a couple of years. So there's those concerns, should we say, in terms of the potential, and again how this can be used. Quite a bit of the information that was looking at the process and at the design aspect, should we say, as well as the activities involved to try and control the human element. So I guess from an engineering background, one of the things that jumps out at me is the standardization that takes place between manufacturers and suppliers. So what I mean by that is, rather than it being unique to each company, that the same hose pipe in this case can be connected to a different nozzle or connection point, and therefore there is that opportunity for mistakes to happen. Nowadays, if you look at petrol stations, you've got the difference between the nozzle for a diesel and the nozzle for a petrol, unleaded petrol going in. And this is as a result of the number of times whereby people put the wrong fuel in the tanks. And as a result of that, it's required, £400 or £500 in some respects to empty the tank and then clean out and then do something with your engine manufacturing system and engine management system to reset everything. And then once cleaned out and reset, then refuel, and that can take time, and obviously it's costly. But there's been many incidents where that's happened. Now, the nozzle of a diesel will not go into an unleaded vehicle car, and then similarly, you can't get it wrong the other way around. The nozzle of an unleaded car can't go into a diesel because of the shape and the design of them. So again, the standardization has thought, well, we need it to be easy for users, operatives, and others to interact. But at the same time, this has led to, as it did in this case, the opportunity for human failings. Particularly as you saw the proximity of one next to the other. Perhaps the connection points should be a lot further apart, should be better labeled. But if you had a particular design of nozzle or connection point that only went onto one type, and then it can't be done incorrectly. Similarly, the other causes that after the event, what went wrong now that we have created, in this case, chlorine gas, which can be fatal. Having created that, what's your response and how effective is your response? Because then it comes down to designers and then the people using the system to be adequately trained and competent to be able to interact with that, so that they can hit these emergency valves, emergency switch points in a convenient way and in a timely manner, so it doesn't lead to a bigger scale disaster. So there are things around that perhaps can be put in place now. Even if it's as simple as let's say a Bluetooth system nowadays that's on the technology that's out there for an app on your phone, so that you can immediately react, even if you're remote. As soon as you're alerted to a particular problem, you can do something in a smart way on a smartphone. So there's those aspects around it as well. So I thought that was a good way of starting off to show where we're going with this and the impact it has on disasters. So then I can come back to the accident causation theories and then move forward with that to say, learning from disasters. Everything that's happened has led to our interpretation, and therefore we can use that to prevent further incidents from taking place. So the view leads to a number of general assumptions about accident causation. Firstly, the likelihood of an accident is a function of the total numbers of pathogens, those latent failures we talked about in the previous section, resident with the system. Secondly, there are more complex, interactive and opaque the system, so the variables and the misinterpretation, should we say, the greater will be the number of resident pathogens, problems associated with that. Thirdly, the higher an individual's position within an organization, the greater his or her opportunity for generating pathogens. Now, this is, for me, it's a key point. It's that management failings, should we say, rather than human failings, but management failings put the appropriate time, effort, and resource into controlling risk. And again, as we said in the previous part, it's about that latency and that attitude and culture that's been allowed to develop because they've not given the true respect and time that they should do for the level of risk involved. And then fourthly, virtually impossible to foresee all the local triggers, though some could and should be anticipated. So if you've done your analysis effectively, then you should have been able to branch down and identify where those failings can take place. Resident pathogens, on the other hand, can be assessed given adequate access and system knowledge. It's the what if scenario. And if you're constantly analysing where things can go wrong, and even if the designer got it slightly wrong, perhaps the design can be modified by someone later on so that efficiency is improved, but safety is improved in somewhat in a radical way, but nevertheless not being risk averse. And what I mean by that is some companies are averse to making changes to systems and procedures, particularly from a warranty, should we say, or a guaranteed piece of kit. And they will say, well, if the manufacturer supplier hasn't installed it, then who am I to come along and change that design? Fair point, I guess. And some people would be risk averse and say, what I'd rather do is pass it back to the manufacturers and designers and installers and say, this is not quite as we want it. Make amendments, make changes that are effective and safer. But you can take it on board yourself, but many companies that are risk averse avoid that. But at the same time, they point the finger. They point the finger at the installers, the engineers, and the manufacturing suppliers, rather than saying, well, actually, I've lived with this design for X amount of years and I've put up with it when I should have done something about it. So there's those pathogens, the resident pathogens that are around. And therefore, the efforts of safety specialists, your safety bods, who are out there to try and focus on these issues. Interestingly, what we're saying is it could be that the safety specialists could direct more profitably towards the proactive identification and neutralization of those latent conditions. Spend the time, effort, and resources themselves as a specialist to say, we've looked at the what ifs, we've looked at the engineering, we've looked at the process, we've looked at the interaction of the people as such, and we find there are gaps or holes whereby that trajectory can go through. Now, rather than focusing on the prevention of the active failures, perhaps we should focus more on neutralizing this, redesigning it, puts better safeguards in place that doesn't rely on things that can go wrong. Therefore, reliability comes into it, and that's a part of what we're going to be talking about today. And then in this next session, it'll be focusing on, once we've provided something, the importance of maintaining it. So if we say we'll put something in place under Pure that is fit for purpose, then there are aspects of Pure that says it must remain fit for purpose, and therefore maintenance and activities around that, servicing, testing, and so on, become a part of a manager's responsibility, but the safety board can spend time looking and measuring and monitoring that manager, as well as the process and as well as the system and as well as the engineering of it, to then check. So you have some means of measurement in place, maybe the KPIs in line with the COMA regulations as a classic example. But once those have been put in place and you monitor it, you can then use that as a target, and you can also use it as a stick, should we say, to start moving people forward in the right direction, to avoid these latent issues and the culture that develops as a result of not responding effectively and timely to potential incidents in the workplace. So that was, in itself, for me, those 4 key factors are important, and then therefore the impact associated with it. Reason identified it, that there are shortcomings with this, because at the end of the day, it's an analogy, and therefore it's not based on functions. And from that, it means that there's some feelings, should we say, it's a bit vague, and I'll go with my gut instinct rather than the function specifying and being measured that says it can't go wrong. It's based on the notion of causality. So, that has its limitations, because if you don't identify all the causal factors, then you could have missed an opportunity, and it still has the potential for things to go wrong. The failures and deviations are focused on rather than normal working. So some would argue that even though a safe system work or a standard operating procedure is written, do we actually follow that? And is the safest method being followed in the normal working conditions and the activities of operatives? So it really is a fair point there. And then there's the overzealous implementation. So people just want to get to production too quickly, and they've invested a lot of time in this kit, this equipment and the machinery. Therefore, right, let's get the money back from this as quickly as we can, rather than testing it out, rather than checking it. And therefore they'll perhaps, I guess it's linked to decision making. And if it's high investment linked to decision making, you're more likely to prove yourself right and stick by your guns, rather than allow yourself to consider, I might not be right in this area, or I might have got it slightly wrong, and maybe the kit that we're buying isn't quite fit for purpose, and maybe it needs to be modified or changed and so on. So that overzealous implementation sometimes can lead to the illusion to management, and therefore there are errors that are perhaps not going to the attention of management for fear of the finger pointing, or for fear of getting it wrong, or just trying to look good in front of others. So there are those aspects of project failings due to the people involved making a decision and wanting to say to others that, look at me, I'm good at my job. So there are errors associated with that need to be thought about. And similarly, active errors may be the dominant factors in the workplace as such. So many of these errors are simply the byproduct of normal, adaptive, cognitive processes, similar to what I was just explaining. Inadequate defenses would make the errors more dangerous, but even then, some errors would overcome even well-planned and maintained defenses. Yeah, so again, it's people wanting to look right and making decisions. Once they've made the decision, being stubborn about it, rather than accepting, well, actually, there are better ways of doing it. There are safer ways of doing this. So we have to consider that the causal links between distant latent conditions and accidents are often tenuous. So again, learning from hindsight is good. If we have enough knowledge and experience in these areas, you can predict perhaps what these potential problems may be, and then put them right before they become a latent condition. Those latent conditions can always be identified with or without an accident. So what we're saying there is, don't wait for an incident to happen before you do something about it. Be proactive. And some latent conditions may be very difficult to control or may take years to address. And that's very much about culture of the organization and their ability to respond to change. A misapplication of the model can shift the blame backwards. Yeah, so again, it's like, now that I've got it wrong, I've lost face with people, that my position isn't as credible as it used to be. and perhaps they don't now see me as a competent person giving accurate advice. Therefore, that blame backwards means that there's reluctance in taking on board the expert's opinion. Even this morning, I was watching the television, and the words were, "If the scientists have got it correct," you know, that's a classic example of wanting to challenge someone. So they were talking on the news about Miami, that parts of Miami are going to be underwater in the next 3 to 5 years as a result of climate change. And then the news person said, "If the scientists have got it correct." So that what they're doing perhaps is covering their own back to say, it's not me saying this, it's the scientists that have said that the information leads us towards this decision. But for the punter, for the people watching that program, they're now challenging whether this is actually theory, which could be wrong, rather than this is what is going to happen in the next 5 years. And therefore we've got the next 5 years to put it right. So there's those kinds of attitudes and the way things are presented that can affect and cause this blame backwards movement. So then Perot came up with this theory about normal accidents, and it has this system approach to it. So in the interpretation, accidents are natural occurrences because of growing complexity of the system. So misinterpretation could be a classic example of that. Tight couplings and the concomitant human inability to understand. So the collective decision making that's led to that point in time makes humans unable to understand them or put them into place. And I guess from the CSB video we saw earlier on, you can see there that perhaps the systems and procedures are in place, but the people who are going to have to react effectively didn't respond in the manner expected. So perhaps what we need to do is change the system so that it reduces the human error somewhat. Barriers and redundancy introduced to limit accidents have added to complexity and increased opacity. So the vagueness comes in terms of interpretation of a particular way of doing things or a system as a result of it being complex. And therefore, the simplistic approaches make it as easy as possible for people to understand and apply, so the vagueness or the opacity cannot be misinterpreted. Humans are unable to control them directly or indirectly. So yeah, the outcome happens, the accident has taken place, and therefore, regardless of what we put in place, it has a direct or an indirect impact on them. And that's rather than a zero tolerance on accidents. What we're saying is accidents will happen anyway. So where that can be the case, what you've got to focus on in mitigation in terms of risk management, the extent. Okay, you can't control the likelihood of this happening much, but what you can do is look at the severity and reduce the potential severity associated with. So the what if it's going to happen, what can the consequence be? Can we mitigate the extent of the consequence? Complex interactions are those of unfamiliar sequences, unplanned and unexpected sequences that are either not visible or not immediately comprehensible. Now, this is an expansion, should we say, of the health and safety executives' interpretation of an accident, you know, an unplanned, unfamiliar event that results in. Yeah, so what we're saying here is the more complex it is, the more chance there are for these incidents to take place. So they're not immediately comprehensible. They're not easy to interpret and implement. Tightly coupled systems have more time-dependent processes. Yeah, so if you have one system next to another, there's no gap. There's no time to avoid failure. Reaction time, should we say. The sequences and coordinated activities needed to produce the product are invariant and have little slack. Yeah, so that relax time in between. It's a bit like I was saying about the time and motion person. They've tried to be so efficient that they put too much in there without sufficient rest breaks. So, for example, quantities used in production must be precise and the process must be done right first time or not at all. You get that quite often in manufacturing and process industry now. There's only one way, and we will always do it that way, so that there can't be any misinterpretation. It always happens. But by doing that, you're not taking account of the variables. Complex systems consist of multiple parts that depend on each other, and there is only a limited possibility of delaying processes or carrying out the actions. Yeah, so can you respond in a timely manner? And the more complex it is, that answer becomes no. More evidently, it becomes no, and therefore the more chance for a crisis to come about. Therefore, actions must generally follow in invariant sequence. Think about the variables, and there is often only one method to achieve a goal. Now, if they perceive that to be the case, it could not mitigate, should we say, the consequence. Therefore, you've got to anticipate these invariant sequences so they can make sure that the control measures, the response, mitigates and reduces the risk. And there is limited possibility of slack or of substituting supplies, resources, or personnel. Yeah, it goes back to the one way of doing things that I mentioned earlier. So the buffers and the redundancies exist only as they have been designed into the system and cannot be adjusted to fit unforeseen demands. So it's the key area of the inflexibility here of once you've got a system and a procedure in place that could be complex, as a result of the way things are done by that particular complex system, then it really makes it unflexible, and therefore change or emergency response is somewhat compromised. But often the focus is not looking at solutions. It doesn't consider, in all cases, the recent developments like technology, changes in way of doing things, thinking about breaks and attitudes and fatigue, how that can become part of the human element. What about in the non-normal accidents with the organizational precursors? Yeah, it doesn't cover that in this particular theory or analogy. And as a result of that, if you think of some of the disasters, Bhopal, Chernobyl, and Challenger, they're like excluded as component failures accidents. Yeah, so as much as this particular theory focuses on that unflexibility, ultimately, in all those three cases, it was the fact that it was a component failure rather than people reacting in the correct manner. And alarmingly, banal examples of organizational elites not trying very hard. Yeah, so the culture of the organization that allowed that to take place. So with every theory, there are limitations, and that's what we're saying there. And when we look at accident causation, it has an influence on the way that we think, and therefore when we adapt that way of thinking to the culture of the organization, sometimes you have to make sure that the culture doesn't allow you to fall into the line with them too much if it's a safety critical issue. So you've got to make sure you remain independent in some respects so you can give appropriate and competent advice. So I want to then move on, should we say, from these accident theories to think about what can go wrong, and if they've done failure mode effect analysis, if they've done fault tree analysis, if they've done decent risk assessments and risk management techniques, then there is some question, should we say, about reliability of systems, procedures, and equipment and materials. And therefore, the theories they're now leading towards is the higher the risk, the more reliability of the kit and the way it's used, human factor, and the controls that are in place that we rely on comes together. Therefore, high reliability theory focuses on that. It's many of the systems that Perrow describes earlier, but it looks at potential impact. And interestingly, in some of the high-risk industries, they are quite remarkably free from major accidents. You know, you would expect that there'd be much more incidents that have resulted in crises. And some would argue that it's because they give it that respect it deserves, and they give the sufficient time, effort, and resources into managing the risks. Some would argue that that's not the case, but maybe it's about the way it's project managed, and maybe it's about the way the put the time and effort into perhaps a team approach. So it's not one or two people that could get it wrong. It's, well, they've thought about it and they've thought about it, and several others have as well. And they come up with perhaps a best approach that manages the risk. And that doesn't mean that those organizations are error-free, because each of those industries and organizations have had incidents and have had disasters, but the errors don't disable them. They kind of like say, well, it was inevitable in some respects, but what we're going to do is get back on our feet as quickly as possible, and we're going to make sure that we have better control measures in place to prevent them from happening again. So they really do learn from disasters, or they learn from their incidents, and therefore they're classed as mindful managers. They have the right mindset to be able to think and learn from history. So that leads us on to the idea of resilience engineering. And this is perhaps part of the reason behind why they are successful in these potential failure areas. They think about, is it built as part of the overall project, and everything is included within the resilience engineering. The idea behind this is that on insights, should we say, of how organizations manage successful results in the face of failure. Now, we could perhaps interpret that as sharing best practice in a hindsight kind of way. So they've learned and they've moved on. It focuses on finding out how people manage to produce successful results in the face of failure. Now, some would say that in a crisis, certain managers can handle it better than others. They just take it within their stride, they make the right decisions, and having made the decisions, they can then see it through and check, have a logical approach to making sure that it doesn't get to a crisis level above. But even when it does, they still manage to, in the face of adversity, manage to control the situation well. So it's questioning what's involved in that, and how can we use that. The ability of systems to anticipate and adapt to potential surprises and potential failures. So again, this resilience engineering looks at what if, and are we adequately resourced, and can we prevent it? And if we can't prevent it, how can we mitigate it? So that becomes part of the mindset of the management team. A resilient organization doesn't lose control of what it does, but it is able to continue and rebound. Yeah, so that's within the term resilience itself. Resilience is how quickly can you bounce back after an incident? You know, the elasticity, should we say. Here it's saying the organization doesn't lose control of what it does, but it's able to continue and rebound because they've got the systems, the management systems in place, the people in place to adequately resource the response. And therefore, resilient organizations accept some degree of production and efficiency sacrifice. Perhaps they've got it right. You know, the balance between safety and production, and putting more time working with people on their behaviors, the operatives, for example, in high-risk areas, to make sure that the human element is adequately controlled, but also in terms of design and interface with the humans, it's less likely that people can make errors or in violations of deliberate problems. However, the downside to that is then it becomes more complex. So the more systems and procedures and redesign you do, the more reliance on those, and therefore, hopefully it becomes simpler, but sometimes it makes the equipment and systems more complex. It requires detailed knowledge about the domain and the type of work, as well as good understanding of how performance conditions may affect how function is carried out. I guess the best way that I can define this is what would you do if a really experienced, very skilled person is coming towards retirement and who has all the knowledge and interpretation of how things are done safely? How do you keep that before that person retires? And perhaps it comes down to the system, the procedure works well, and therefore it's easy for somebody to be trained up. Or perhaps you have somebody shadowing that person, and then they're mentored by that expert or guru before they move on. And that way, even though there's a loss of that very competent person, there's less impact on the others because they've adequately prepared for it and thought about it and made sure that the eventualities have been thought about. So it's kind of like key people in key positions. What if? How can you make sure that if that person, just like ISO does really, the idea around systems approach is that if a person is not available, they're on annual leave, they're off sick, whatever the reason is, can the system dictate and take over so that there's not misinterpretation, there's not misuse, there are not errors, but the production carries on, or the system carries on, or the people carry on providing the service whilst that other key person is absent. And I guess COVID has identified some of the concerns around that now, but you could also argue that with the internet and with the flexibility and the hybrid working now, quite a few people would accept there are better ways of working, and with the support, should we say, of these applications and systems that are online, there's less error because of it, and it's quite efficient. It lacks a body of practitioner knowledge. Yeah, there is always that potential for a gap that could come about. That lacks a working model and is difficult to interpret. Again, more complex you become, the more chance there is for misinterpretation. And then there's the question around, do we have sufficient examples and historical information that proves that this is the way to go? So there's some question around activities that take place. So I just wanted to reflect on and finish off with the accident models that we talked about earlier and look at the impact that they have. So stereotypical ways of looking at accidents can influence us in the wrong way. So try to be adaptable. Developments in accident models may reflect changes in industry and its organization, but sometimes they don't. Then don't always take account of, say, technological advances and ways of doing things. Each of these models have their own strengths, but they also have the limitations and weaknesses. So I would argue, what model do you try to look at and use? And perhaps think about that. Maybe if you've got enough in your team of accident investigation, maybe you need to consider the other aspects of, multi-causality, should we say, as one example. So we'll move on now, where Holnagle, I've finished in the last session, just touched on a little bit about the research done by this gentleman, but it's gone further on from this. So explanations rather than causes were involved in that and how we've used it. So accidents are characterized as a series of events, each with their own sharp end and blunt end that come together in an unpredictable way. So what we're saying there is you can see an immediate response, an acute condition. Sometimes the blunt end is those chronic conditions that, as a result of several incidents happening, it's linked to a chronic situation. And in both cases, they are somewhat unpredictable. Therefore, they're not simple to understand. And sometimes the development and progression of them is hard to pinpoint. So the responses of the system are non-linear. Think about the rock opposed to the bird as such, and therefore the variables, so that can impact, which means that the effect or the output is not proportional to the cause. And therefore, just because others have had similar accidents in the past that haven't been severe, it doesn't mean that we can then predict low risk or medium risk. We've got to think that in all variable situations, particularly in high risk environments, the what ifs and plan effectively, rather than having this, I guess some would say success breeds contempt. Yeah, so don't allow non-incidents or non-reportable incidents have been reported for 5 years, and therefore we've got a very good safety record. Just don't just focus on that, because it could well be that, well, we're just waiting for an accident to happen, and at some point that's going to all go because we'll have one severe incident. So keep monitoring, keep on top of it. So the constant accident model kind of looks slightly different to the other models we mentioned before, and therefore it takes account, as we saw with multi-causality, technology, equipment, human performance, organization in that linear fashion. But what if something happens, then there must be a cause, but also, rather than just focusing on the cause, think about what conditions are in place at that time. historically that led to it, but also what can we do in the future to prevent it from happening again. So he takes it that further. The search for explanation is often based on the incorrect assumption that explanations can be deduced from the facts. Thus, accident explanations and the search for causes are very often just trying to fit all the facts together. And I guess it could be, in some respects, you know, we go into an investigation, we get a little bit of information, and it starts to direct us down one particular path. I always say to people, remain open, don't make too many judgments early on, allow the facts to speak for themselves. But carrying on from that, where it's saying trying to fit all the facts together in the belief that there is some kind of objective truth to be found. Yeah, we want to come up with some solutions to a particular problem. So it will, therefore, we will produce that information. Not all the facts may be evidence. Something may be missing, and we have to accept that. Also, some data may not be facts, but just spurious observations. So you have to be able to delve into it and say, well, that's an interesting point, but I don't need to do anything with it at this stage. However, it's useful to be able to give you a general interpretation and understanding of management, culture, and decision-making. So spurious observations that are causally unrelated, although temporarily contagious. Finally, the facts such as they are not independent of the accident model. Yeah, so do we allow the accident model to lead us down a particular path, or are we open to other ideas as well? Indeed, facts themselves are not found but sought out. So comes back to the fact, yeah, can be deduced from the fact. If we can't deduce it from the fact, there might be other issues that we can look at as well. Performance variability, yeah, rather than going in a straight line, it's all going a bit about that, but ought to be able to interpret what those variables are. At the sharp end, those people are determined by a host of factors. The backward search for the cause is likely to reveal a complex network rather than simple cause and effect chain. Emphasis that accidents analysis must be based on an understanding of the functional characteristics of the system. It advocates a search for usual dependencies and common conditions that, from experience, we know are associated with accidents. And then finally, the best option, therefore, is to monitor the system's performance so that potentially uncontrollable variability can be caught early on. Yeah, and I guess that's where the culture aspect comes in, really. The more time and effort is put into the way we make decisions and the way we act in part of the process, and then the supervision and line management overseeing that to make sure that the best behaviors are in place to avoid these issues. So coming back to resilience again, these dimensions that we have is preparedness and anticipation. It takes account of the what ifs. Is the organization proactive in picking up on evidence of developing problems versus only reacting after problems being significant? Proactive compared to reactive. Opacity and observability. Does the organization monitor safety boundaries and recognize how close it is to the edge in terms of degrading defenses and barriers? And to what extent is information about safety concerns widely distributed throughout the organization at all levels versus closely held by a few individuals? Now, if you look at an HSE investigation, particularly in high-risk environments, typically after a fatality or a serious incident, before they come to a decision, they spend quite a bit of time looking at this. How are systems and procedures adapted? What is the attitude by management? What is the culture of the organization? And how does it influence the decision making? And then they'll start to question things about where is the money spent? And can we see the evidence of where the money is spent on health and safety related risk controls? And the evidence will speak. That's what we're saying here. Their evidence will speak, and therefore it makes it easy for them to make their final conclusions and therefore the recommendations, and in many cases the prosecutions. I try to use that with companies when I'm saying that your attitude needs to change, your culture needs to change, and we're not going to change it overnight. We need to work with all levels of the organization, the people, to get them to adapt and change in line with the culture requirements. You need to think about revising and fixating aspects of how the organization changes and responds, should we say, to different models and vulnerabilities associated with it when they're putting those changes in place. Detecting the signs of increasing organizational risk, especially when production pressures are intense or increasing. For example, cross-checks are working effectively. So how are we monitoring? Are you doing inspections and audits? And from those inspections and audits, what is it telling you about the company? And particularly in high-risk environments, how do we need to change or respond? Having the resources and authority to make extra investments in safety at precisely these times when it appears least affordable, because it's used too often. We can't afford it at the moment because of current position in the marketplace or other issues. However, every budget that's put out has an element of safety within it, and you shouldn't have to justify it, but quite often you end up putting reports together that justify investment. That to me says that if you're having to spend a lot of time on justification and cost benefit analysis, it may be that the engineering side of it or the resilience is not there for the putting it right and maintaining it to be right and relying on that rather than having to justify the money. Having a means to recognize when and where to make targeted investments to control rising signs of organizational risks and rebalance the safety and production trade-off. Now, many companies have a risk register, and it doesn't just have health and safety in there. It has, reputation, financial, IT related, other issues that are considered risk to that company. But what it's done is it's put to the board, the senior management team, and it made sure you get the right approach from it. So somebody has to analyze that. And it's not always the safety board that does this. It's quite often, somebody in a high position, a registrar or someone close to the board that can then say, oh, we've had these incidents this year. And as a result of those incidents, we have to put that on the risk register. So they're constantly reviewing where that position is and what they have to do. So those trade-offs could be balancing safety, should we say, to make sure that there's not a reputational impact or there's a serious incident that could stop work in the future or could increase the potential legal aspect of it and legal investigations. Farmer and Chambers have the accident proneness approach. So they examine the accident records of a large group of drivers and found that a few, again, had more accidents than other people. So there's an argument here about proneness to accidents, and that's what they were doing as part of the research. They used personality tests, psychometrics and such to try to identify the personality traits that might account for this apparent tendency. And some would argue that it's not just proneness, it's clumsiness, for example, is a condition that's been argued by quite a few people. And if it's a medical condition, which it isn't recognized that way at the moment, but if it was medically recognized, perhaps more time and resource will be put into that to prevent. But nevertheless, that's one of the areas that we look for in this proneness aspect. Although they found nothing conclusive, they were still convinced of the existence of accident proneness. A personal idiosyncrasy of relative permanence predisposing the individual who possesses it to a marked degree to a relative high accident rate. A couple of companies that I've worked at, when we look at accident records and trend analysis, and quite often I don't use it in the safety committee meeting, but I do know that some people have had more accidents than others, and you could argue that it's their attitude towards work. You could argue that perhaps they're under stress or more likely to be suffering from fatigue during that particular life part. For example, a parent of a child that's relatively young, the lack of sleep that they're getting because maybe the child's or the baby's routine is affected. That impacts on that individual, and we're prior to having a baby and then having a family, should we say, and during the early stages of a family years, then you could argue that they've changed somewhat, and rightly their focus is more on family perhaps than it would be on the job, and as a result of that it could lead to accident proneness because they are distracted or they are tired as a result of that. So errors can occur more often. Further from that, in their research in this area, since this has failed to find any overall stable profile of the accident-prone person, it did hit a few hiccups. Therefore, it was taken further by Glendon and McKenna, who cited research that seems to show some more persuasive evidence, because they were looking at drivers in particular, as to why some drivers have more accidents than others, or they were more prone to have accidents. So it does seem that there is some theory on this. However, it's not been fully proved, and therefore it's not got the standing it perhaps needs to have from research fields. So it seems that there are maybe a number of factors that may predispose people to having accidents, but the stability of those factors in any one person is questionable somewhat. Reason then went on further in developing accident prevention theories. Examination of accident repeaters over a lengthy period indicates that they are members of a club which is continuously changing membership. Yeah, so you know, going back to proneness, there are elements where some people are more likely to have accidents. New people are added to this club, yeah, while long-standing members cease to qualify because their boundaries perhaps change, but as they've had accidents, they've now changed themselves. You know, they're more fear of, or as I always say, I'm allergic to pain, you know, and that affects my approach to risk as such. And I guess certainly talking to my wife over a few occasions like this, when she was young, she used to do quite a few different sports. She loved skating, she loved skiing. She wouldn't do them now, because now that we have a family such, there are worries that if she has an accident, that it will impact on her ability to, you know, provide as such. And in providing, it's not just money, it's providing the service of being a mum and being there for them when they need them. Those kind of issues. And I guess I've changed as such. I used to like driving fast, and sometimes I would breach the 70-mile-per-hour limit on the motorway. Nowadays, I'm affected by economy and also the impacts on the environment. And I think what I should be driving around, and I don't always comply with this, but I should be driving around at say 55, 56 miles per hour whenever I'm on a motorway. Now, if I've planned it right and I don't need to rush to get there, I will now make that conscious effort of driving between 55 and 60 miles per hour, knowing that the cost of petrol is having an impact on my decision-making process, but also thinking about the safety aspect and my ability to be able to respond effectively when there's a potential crash or somebody makes a mistake, as happens quite a lot on motorways. Lawton and Parker take it further, and there's a CIR document on this, quite a lengthy one, 175, and they did it in 1998. But they looked at it even broader in terms of accidents as such. So little evidence to support a grand theory of proneness, but accidents can arise from two different classes of behaviour. Cognitive factors, it being one, so the attention capacity, the perceptual abilities and knowledge, and then you've got deliberate risk taking on the other side of it. So they explained by a consideration of attitude and motivational factors. So personality factors such as extroversion and introversion. So are you outgoing or are you quite reflective, may have a role in both errors and violation. So it is a lengthy one. If you get a chance, have a read of it, because there are some interesting parts of it, particularly when you look at the psychological aspects of making decisions when posed with risk. But also, they came up with the two types. We'll have a look at proneness. The first type is temporary state resulting from stress or life events. Yeah, so things that have happened in the past that make you act in a different way or a particular way. And then the stress in itself, at that time, you're perhaps in survival mode, so you think differently. And then the second one is that stable trait. Where do we go to normally, cognitively, in our decision-making process? The repetitive nature of ourselves. How do we respond to that? And it could be that in terms of accident process proneness, some people make the wrong decisions too often, and therefore they put themselves more at risk as a result of it. So the stable trait looks at what if and where do we go to when that happens in our head. Some people's decisions are more risky than others. Okay, I'll move on now to socio-technical systems. All work systems require both a technology and a social organization of the people who use that technology. This impacts on culture, so it is important to try and consider this within safety and risk management. These different components are at the same time independent and dependent, so interdependent, should we say. So there are ways in which it affects our interpretation of that. When we look at loss integrity, particularly of materials, it affects, and there's been quite a few incidents where these have gone wrong. So component parts have led to those incidents. These incidents create substantial direct and indirect losses. Obviously, you've read through these, I would have heard of them in the past, but those losses are impacted on the organisation, financially, reputationally, as well as being in the eye of the HSC and enforcers. Its employees and members of the public were affected. So there's this psychosocial impact there as well. And as a result of failing, should we say, of materials, we have to look at the materials that are used in a variety of different plant and equipment and how they can, or even then, be more prone, should we say, to things going wrong. So part of this is to look at integrity of structures and the materials that are used. And within that, when we say fitness for purpose, it's a term that's used a lot in engineering and also under PUR regulations for work equipment. When you demonstrate that something is fit for purpose, usually it's been tested, it's been tried, or it's historically, it's got the research that backs that particular material on that pipe or on that safety valve or on that particular process. Stainless steel, for example, will be better than mild steel, where there's potential for some of the materials going through it or weathering on the outside of it could cause corrosion, so, as an example. So you look at it and get the balance right from hopefully it's safety first of all, rather than the economy. And in one of the disasters, and I was doing some research and reading through the CSB one, they'd done exactly that. They'd taken out a stainless steel pipe and replaced it with mild steel, not thinking that the acids that were going through were going to corrode it very quickly. And as a result of that, it was ball pelt, wasn't it? As a result of that slight change and cheap approach, economy, led them towards a disaster. Regular checks once you put something in place are necessary. So whether you class this as maintenance or servicing, for me, it's more monitoring and inspection. And historical information will tell us, as I said at the beginning, that certain materials, certain equipment will last for X amount of time, and therefore a preventative maintenance program or programmed preventative maintenance, whichever way you look at it, it states that those parts, those components, those materials need to be replaced 6 months, 12 months, 2 years, however long it says in terms of its life cycle or expected life cycle. But don't just take it as read. If it says 5 years for a particular piece of equipment, don't just say, oh, I can sit back now and do nothing. You still have to monitor it and inspect it and check it that it still remains fit for purpose. So that concept involves a wide range of disciplines: the designers, the fabricators, the material specialists, the chemists, the analysts, the plant users and operators. All of this comes together to be able to get an understanding of the limitations of particular pieces of materials, equipment and component parts. And we use that information to make those best judgments on reliability, credibility and structural integrity. So think about your means of escape, and all means of escape should, if it's a corridor, for example, leading to a final exit door, they should offer 1 hour fire protection. Now, we've not just said off the top of our heads that plasterboard can offer 1 hour protection. No, it's been fire tested. Somebody's put it in a lab situation and in a real situation. So they've set up a house kind of room environment and they've put that under fire situations. And as a result of the plasterboard on the walls, they can say plasterboard offers typically 4 to 8 hours protection. And then you look at variations on it. So that's an example, should we say. And the ideas are put in position there to help us make these responses, decisions effective. It looks at materials' ability to withstand certain forces. So if you think about destructive testing, the information is used from that, and sometimes non-destructive testing is used in the various environments. It looks at the history and the information about different types of machine plants and buildings, so that when they are designed and made, they're considered to be capable of resisting the forces. Now, it could be the elements of weather, or it could be the fact that there's vibration coming through from an area next door or another plant or equipment. And therefore, what do we need in the foundations? Is it just basic concrete, or do we need it to go deep with rebar and concrete to make sure it offers the correct foundation that doesn't allow vibration to transfer, and so on and so forth? So it looks at those aspects in terms of the wide concerns, and then making sure that we make the decisions so that the machine, the plant, the equipment, and the buildings can withstand or are capable of withstand the variations of different forces that are applied at that time. Any load applied to a material induces stresses and strains, and questionably would say how much of that can it return back to its original state. So if you think about thorough examination, for example, in lifting operations, lifting equipment regulations, if we use a chain as an example that's been used in a load lift, if the link, should we say, is a typical shape, kind of like that shape, maybe it's stretched, and by visual inspection you can see that it's not the shape that it should be, and therefore is it capable now of doing the job it did before? Now, usually when you see a change in the physical state of it, it's because it's been induced with various strains and stresses. And it could be that when the chain was being lifted, rather than it being a nice flowing movement, it was under jerking pressures that's gone to the weakest link in that chain and stretched it. So the need for inspections, checks, and thorough examinations are necessary to look at the problems. So within that, and I've used a chain there, and I've talked about elasticity to some degree, it's about the material to withstand deformation. So when it does have a strain or a heavy load put on it, it will withstand that and stay within its natural position and shape, or does it deform? And if it deforms, it's because of the stresses and strains it's been put through, and therefore it's changed the properties of the material and created, in this case, if I'm talking chains, a weak link, and therefore the chance for an accident. Materials have a different modulus of elasticity. So we know this from years of research, mechanical engineering and so on, and it can tell you basic information of what it's capable of withstanding. It puts these materials, various materials, on these testing to check what it's capable of reacting. So it's tensile strength, it's compressive strength, it's shearing strength, bending and torsion strength. So in order to do that, it proves integrity. That integrity affects reliability. As a result of that, you can then say that material can be used in this process under these strains and stresses, and should withstand what I class as a safe working load. Hence, when you do use it for lifting equipment, it indicates the limitations of the weakest part of that particular lifting equipment. So you might have an overhead crane, gantry truck crane, that's capable of lifting 5 tons or even more, and it's got that written down as the safe working load. But then you've got the hoist that's connected to it, may be limited to carrying 1 ton, and then you might have the hook or maybe a shackle that attached to the hook or the chain, and you look at the information and it's limited there to say 1/4 of a ton. And as a result of that, you need to make sure that people can then say the weakest link says the maximum we can lift with these component parts is 1/4 of a ton. Otherwise, when we do put it under these various strains and stresses, it's likely to stretch and break and fracture. So whilst materials may have differing strengths, the way in which they react to the forces is quite similar, and there's an expected interpretation of what that material will do. And we use that so we can say, design in a building a load-bearing beam, for example, and as a result of the shape of the load-bearing beam, under typical conditions, it can withstand 25 tons, for example. And therefore, if you've got that beam in a place whereby the roof or the activity above that beam is going to be limited to, say, 10 tons, it makes it structurally integral, sorry. Application of loads and subsequent removal should see a material return to its original shape as long as the elastic limit has not been exceeded. So that's the general theory there. Exceeding the elastic limit will lead to a permanent deformation of the material, and materials display very different properties in this respect, considering glass against copper. So glass will shatter, copper will stretch and eventually give way. Plastic will respond in a malleable way, but also dependent on the conditions. But in its malleability, it has a lot of strength, but eventually when it does go, it cracks. So these relationships are put together on a steel test plate, should we say, if we're looking at integrity from that perspective. And it has load on one aspect. So the more load we put against it when we're doing these tests, we're looking at the response and the extension going back to elasticity and whether it refers back to its original shape. So the more load that we put on to it, eventually we'll get this fracture. So the ductile failure of it. However, it is a typical arc or shape that it responds to. First of all, it hits the yield point where you start to see the modification in the shape, and it will start to stretch. And that's known as the yield stress against it. It's more plastic in the way that metal responds, or steel responds under those loads. So what you see is it's stretching out. It's still intact as such, but it's stretching out and deforming. It goes from the yield to the yield stress to the ultimate tensile stress. And the ultimate tensile stress is where it starts to accelerate the speed at which it will fail. So it stretches faster and longer. So you visibly see that, and eventually it breaks. Right. So in some steels, when they're under these stresses, it can take as little as 3 to 5 seconds. On other stronger steels, where they've been treated correctly and they've normalized some of the stresses and strains inside that, so it's been heated up and it's taken some of the stresses out, or it's been malleable tested and so on, eventually it gets to a stage whereby you know that is a lot stronger, that makeup of steel, stainless steel for example, compared to mild steel and the variations on it. And then if you've got compounds of different types of steel where you've got more bits and pieces in the makeup of it, it can either make it stronger or make it weaker. And therefore on the graph, when they put it under load and they do this test, they can see that graph appearing, and it will either be a short time under a large load and it fractures, or it can be a large load for a longer period of time before it fractures. And therefore you get to know about the integrity of that particular piece of material. So once we have all this knowledge of it, and it's been tested over years and years, and you can see that common ground, we can use the information in those tests to then reach a conclusion. And then designers and manufacturers use that information to be able to say, what's the best material to use in that particular spec on that project when we're building or when we're fitting that equipment, or under these conditions in the workplace, we have to modify this because of. So all these decisions are made as a result of the integrity testing, the information. Now, obviously you don't, once you've tested something and you have that information, you don't want to then destruct it. And therefore there are some methods that can be used that use the information that we know about these materials to a degree, and we use that as part of the judgment. But then the non-destructive testing allows us to perhaps get inside the material, X-rays, for example, or magnetic particulates. So what you can do is you can put a dye on it, and then when you put the dye on it, if there's any cracks in the metal, then when you put ultraviolet light over the top, you can see the glow where the length of the crack is. And that eventually, with it being non-destructive, you'll say, well, I can accept parameters. So if the crack's only that long, it's okay. But as soon as it gets to that distance, that means it's unsafe. And therefore, we've got to take that out or replace it. So there are other non-destructive testing methods that are available that when they are in situ, that are used regularly by thorough examiners under LoLA to do those tests. They also, if you take a forklift truck as an example, they will also put it under load test as well. Let's say the forks, one of the weak spots on forks is the heel. So as you can imagine, the L shape, it is the bit where it's just bending round. And it can, in itself, it can stretch and cause a crack if it's under too much load. So if drivers and operators go beyond the safe working load, you're going to get that potential crack growing. So they'll do the thorough examiners will do a visual inspection, and if they're not happy and they see a slight fracture or a crack on the heel of the forks, they might then use these techniques, non-destructive techniques, to see whether it's acceptable or not. And if they're still not happy with that, then they'll put it under load. And they'll say, well, the safe working level of this, let's say, is 3 tons. So it can lift that under 3 tons. What we'll do, based on the safety factors, we'll put 3.5 tons on it. And if it is okay after that test, we'll sign it off. But if it then shows that the crack is opening up, we'll then say, no, it needs replacing. So integrity testing plays a part as well. So when we provide something that is allegedly fit for purpose, we need it to remain fit for purpose. And under regulations, the LoLA regs, there's that aspect of making sure. And it's similar with the pure regs. Any work equipment as such has to be tested and checked on a regular basis to remain fit for purpose. So, and that's part of what we look at in terms of reliability. Probability of failure. For many components, early life involves a higher risk of failure. So think about running in, as an example. Cars and engines needed to be run in as such before they were then sent. And sometimes the manufacturer would say, I need you for the first 500 miles not to exceed 50 miles per hour. And then when the engines run in, we know it's capable. And what they're saying is, it could be something in the makeup and the design of it, or the putting together of the engine that might go wrong. But after that 500 miles, it's unlikely to go wrong at that point. So keep to a safe speed so that if it does go wrong, it's not going to be a fatal impact. So it thinks about reliability of failings and then predicts them. But not all materials or components display such a failure profile. Some are predictable, others are not. Early problems may be due to fabrication or design errors. It may not have been put together or fused together in the extent expected in the engineering design. So it's down on paper as a technical drawing, but the person who's manufactured it may have varied from it slightly or made slight different changes on the materials, or has used a different technique to fuse the metals together as such. And as a result, it perhaps is not as strong. So some of the problems came about as a result of that. Early life of material components may be covered by warranty by the manufacturer. And that's why they have a warranty in place. So they say, we're pretty sure that in the first year or the first 6 months, there's not going to be too many problems. However, if you do get a problem, just return it, we'll replace it. That's common practice in many things. Now, if we think of electrical components and with the link to PAT testing, many companies say there's no point doing a PAT test in the first year because I've just bought it and it's still under warranty. After the first year, then I'll start doing PAT testing. So great, fair enough, I understand that one. But as time passes, the onus shifts to the owner. And even if you have at one point said, well, it was credible when I bought it. You can't just say 3, 4, 5 years on, it's still as good as it was. There is the chance. Only clear way to avoid problems is to adapt a planned preventative maintenance program. And by doing that, it will identify those issues. So all materials and components, no matter how well designed, may be subject to failure. Any investigation following a failure determines the mode of failure attempt. Modes of failure relate to the type of stress which the material has been subjected to. So there's that in the thought process, thinking about tension, compression, shear and torsion, as we mentioned earlier. And sometimes failure may simply be due to repetition and not through overload alone. So because of that, we expect failures. Ductile fractures associated with tensile and compressive stresses. So it's made it more stretchy and it's deformed. And therefore substantial plastic deformation prior to eventual rupture involved. So what we're saying is before it actually fractures, you can see the misshape of it, the deformation of it. And as a result of that, you can take action. Buckling. If you think of a buckled wheel on a bike as such, it resulted in that because maybe one of the spokes was under more pressure than others. Classic example here as to what happened, but it can be an unstable compressive collapse of structural members such as scaffold. Yeah, think about the fact that shaping of the scaffold, the uprights and the transoms that go across, but sometimes they have cross bracing, and that cross bracing will make it stronger, so you can put load bearing areas in place. But even so, they will fail after a while, because if you think about the portability of scaffold, it's used on one site for a week, it's taken down, bang, 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 it's put back up again, bang, 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 it's taken down and after another week and so on. It's got to have an impact on the ductility, should we say, of the strength of the material, and therefore more likely to fail the longer it's been used. How brittle is it? And looking at the aspects around that, so that when it is put under a tensile stress, so maybe an impact issue, is it brittle? Does it fracture and break, or does it just bounce around a bit and it absorbs some of the shock? So there are aspects around that we look at to anticipate failure. Creep. So I guess in a body, it's a classic example of this. So crepitus, the creeping of the joints. You can hear the joints crack as such, or you can hear that gravelly kind of sound that goes on with bones. Yeah, similar kind of things happen in materials and steels as such, used in structures. So in order to think about structural integrity, we've got to think about the potential for things to go wrong. So creep is one of the examples in definitions used for permanent progressive deformation leading to cracks and eventual rupture. So the need for regular visual inspections so that you say, yep, it's still okay, it's still holding its shape, I can't see any stretching or any misshapen as such, so I can still use that, it remains fit for purpose. But if it doesn't, if you see deformation, then take it out of use. The other point there is that if you are subject to higher temperature can affect the makeup of the materials and therefore can make them softer, and creep can come in as a result of that. Where loss of material over time due to frictional and abrasive forces, sometimes due to a lack of lubricant. So, again, a classic one for me is the mortar, for example, between bricks as such. And what you can get is you'll see bits of the mortar breaking off, and perhaps it needs to be repointed. Now, it could be as a result of damp. It could be as a result of water and weathering coming up against that brick wall. And as a result of those abrasive forces, it can change the mortar mixing and cuts into it and bits fall out. As a result, if you think about it, sand and cement is in there. So that if there's not a good bond or adhesive agent that's keeping that together and it gets through the air, the porosity of it. Eventually, the cold, for example, the water that's inside, the cold creates it to ice up. In that freezing, it opens up and swells the gap that the water is inside it. Eventually, it leads to wear, which means it falls off, descales. Metal fatigue, progressive cracking formation resulting in eventual failure due to inability to bear static loads associated with fluctuating loads. Now, again, it could be due to the way it's being pushed and pulled around as such, and that leads to metal fatigue. But sometimes it can be literally where it is standing and the weathering associated with that results in corrosion. And what you will see is progressive cracking. So classic a downspout on the outside of a building, if it was the old cast iron style. Cast iron is great, but it's brittle. And metal fatigue was a problem. Similarly, underground, where you had lead pipes, such fantastic material. Not good for us if we were drinking from lead pipes, but over a period of time, metal fatigue kicks in there. Corrosion, I think I've covered that well enough, but you think about the electrochemical attack of whatever it is, whether it's salted water or other chemicals, it will degenerate the properties. And then we think about fracture and the mechanics associated with it. So if we know the variations on a theme of what makes a material weak, then we need to either avoid those conditions or adapt. Yeah. And when we visually inspect and we see these failings, then we need to do something about it. Yeah. And those are the signs and symptoms that you see: scuffing, pitting, abrasion, fretting, pitting, oxidation, intergranular attack, and so on. Yeah. So we look for them to make sure that it is adequate and remains fit for purpose. At the design stage, what the manufacturers and designers have to think about is making sure that the right materials are used in the right place under those particular conditions. And therefore, it makes it hard for them in some respects, but they have that historical evidence and information that said this is what we used in the past, and it's been able to withstand the test of time in this environment, and therefore it should be adequate. But it also stipulates a life cycle, a typical date at which it's no longer valid. So safety factors are built into that. If I go back to forklift trucks again, even though your typical weight may be of lifting forks 2 ton, there's a safety factor built in that actually it can probably lift 3 ton, but we don't want to tell people that because eventually it'll get a load on it that's 3 ton and it's going to break. So if you only lift it at 2 ton, it's going to remain safe. So at the design stage, it's got to think about all these factors. It's very important to make sure they consider safety and longevity of the material being used, so that if it's not able to withstand that, then we can do something else or use something else. And I must admit, in terms of philosophers of safe design, but materials and the use of materials nowadays have changed. Think about cars as a classic example. You don't get metal cars anymore, because we've now found out that variations on the materials that they use now are strong, they're safe, they're light, and therefore there's a better alternative rather than having a metal version that if we painted over it, it would offer some protection, and however it might corrode, and therefore rust was problematic. I think Toyota went through 15 years of issues around metal on the design of vehicles until eventually they changed over. So designers constantly have to look at these things, but they also have to think about safety. And in higher risk environments, then it's safety critical, because the reliance and reliability is a very important factor. So designers think about safe life, fail safe, and damage tolerant. And this comes down to risk perception, and also it's a bit like a spec on a car. You can get the basic spec, or you can pay a bit more to get the additional bits that make it even better, or in this case, even safer. So the information that should be provided with products and materials and information for users tends to focus on that to be able to allow the user, the buyer, to to make a decision on how safety critical it might be. So SafeLine looks at the design, ensuring through careful design and fabrication that early failure is avoided and limits life to avoid degradation. Fail-safe is a better and higher standard. Design ensures that the system has other load paths available in case of a failure, a backup plan to avoid catastrophe. So if something goes wrong, perhaps mechanically, a chock comes in, so the press doesn't come down all the way. So perhaps you lose energy, and as a result of losing energy, it kicks in a pressure switch. The pressure switch releases, and it puts the chock in position, so the press can't come down and squash someone or damage property underneath. Those kind of things. Fails in a safe state. Damage tolerant is a different approach for designers, because again, you're saying, well, what are you prepared to pay for in some respects? But this design allows for the presence of flaws formed during fabrication, operation, and life, and is based on consideration of fault growth. So company I worked for when I was apprentice, Ingersoll Rand, they eventually designed it, I'll call it a pneumatic tool that you use for digging, you know, your typical cutter, ground cutter as such. They eventually decided to go down this route of a damage tolerant design, whereby they would say, what you could use with this breaker is you could use it for 6 months and then throw it away, because that's all we're going to do. And rather than replacing parts and rather than making it reserviceable, what we're going to do is give you a piece of kit that you can really, really use it, knowing that after 6 months, throw it away. Now, perhaps that's not the best thing nowadays if you can think about the environment and recycling and reuse. But at the time, it was one of the philosophies for designers to consider. And then there's the concept associated with statutory testing. So when you do have these in place, whether it's low or otherwise, it could be gas or pressure testing and so on, that those conditions are checked out. You know, so we've got a couple of examples in regulations there, and I've talked about LOLA to some degree. But electricity at work regulations, you know, the statutory testing for fixed wiring that has to be done every 5 years, as an example, to make sure that it's integrally safe. So the earth bonding strip still does the job that it should be doing, and therefore you get a specialist electrician in to say, yeah, building's still good, we'll come back in another 5 years' time. Cost regulations, when you consider some of the local exhaust ventilation systems that are used to reduce the or extract away at source. So if you're using a local exhaust ventilator, then it's going to remove the fume, the dust, the hazard as soon as it's produced at source and take it away, so it doesn't pass the breathing zone. If you're reliant on that, it needs to be tested, and that could be, if you stick to COSH, every 14 months, or it could be as little as every 3 or 6 months, dependent on the design and the use of it. So let's say in a spray booth, for example, they would have to do it every 6 months because of the level of risk associated with it. I've covered LOLA, but here the need for a thorough examination to be done annually or 6 monthly, dependent on the use of the equipment, and lifting of people 6 monthly. So, you know, service lifts for getting people around up and down a building every 6 months, whereas a fixed crane, a forklift truck, might be every 12 months. Pressure system regulations require statutory tests to be done to make sure that anything that's under pressure is still capable of withstanding that pressure, and there's no defects with it. Similar with power presses, now comes under the pure regulations, but previously it had its own regulation, and so on. So why do we test? Well, we need to make sure that anything we put in place remains fit for purpose. That's the overriding key. But now that we know that things can fail, and we know the symptoms and components associated with it, we need to reduce the potential. So we'll look at the likelihood of it going wrong. That takes account of latent and patent defects. So the latent one is not foreseeable either by location or detectable, and you might have to use invasive techniques or non-destructive techniques. And then there's the patent defect, that defect may be detected by proper inspection and testing. So visual load testing in pressure vessels, it can be literally how tight the valve might be when it's under movement. So those tests play a part in making sure that it remains fit for purpose. When we identify that something can fail, then we need to take action. There's a variety of different tests: proof testing, magnetic particle testing, so we can see where there's any cracks in metals. The proof testing is an actual test of the equipment, safe working load, so putting it under strain. Magnetic testing looks at magnetic flux, and with that, it's looking at trying to find any weaknesses, and the magnetism will generally identify where that corrosion or gap or hole will lie on that. But the good thing about it's non-destructive. Okay, so that's the end of that session on trying to put the second part together on the learning from disasters. I'm going to move on in the next session to look at maintenance, the importance of maintenance and the facts associated with it, and touch a little bit on failure mode effect analysis as well. But thank you for your input on this session, and look forward to the next one. Cheers.